Thank you for the introduction and thank you for the opportunity to speak here. I will be presenting joint work with Andrea Mondino, and yeah, as already said, it's on the equivalence of distributional and synthetic Ricci curvature lower bounds. And I want to take some time to explain what this title is supposed to mean before we get to the math. So for the introduction, we consider Mg a smooth Riemannian manifold. So as you know, locally G is a positive definite matrix that depends smoothly on the point where we're evaluating it, and it induces a distance and a volume measure on the manifold M. And given such a smooth G, we can locally write down the coefficients of the Ricci curvature tensor, which is also a symmetric matrix at every point. And it's given by these expressions. For those that are familiar, the gammas are the symbols of the Levi-Civita connection, which I also wrote down here in terms of G. So what exactly, you don't have to worry about all the indices and everything. What is important about this expression for this talk is that it uses up to second derivatives of the metric G. Okay. So, given the Ricci curvature tensor, we can evaluate it at a point, plugging in two vectors from the tangent space at that point. And we can also define lower Ricci curvature bounds. As I said, this is a symmetric bilinear form. So, given any real number k, we can say that the metric G has Ricci curvature bounded below by k if for any smooth vector fields we can pick a point, evaluate the Ricci curvature at twice the vector field at that point, and compare it to k times the scalar product of that vector field at the point with itself. And if that expression is bigger than that expression, we say the manifold has Ricci curvature bounded below by k. And, okay, maybe why is this interesting? This is interesting because you can prove that manifolds with Ricci curvature bounded below have nicer properties, such as you can control the volume growth of metric balls exponentially, and comparing it to, for example, comparing it to constant curvature spaces, such as, in the positive case, the sphere. And also, I think for positive Ricci curvature lower bound, you even have control over, you get structural results on the space itself, and you learn about the fundamental group. So there are strong implications from Ricci curvature bounded below by k. So this has been something of interest, and one raised the question, okay, what happens if our metric is no longer C2, and we can no longer write down explicitly, locally, the expression or the coefficients of the Ricci curvature tensor, but we're still interested if there are spaces that satisfy something like a distributional Ricci curvature bounded below by k. So there are two fixes for the drop of regularity in the metric G, which I want to introduce you to. The first one is the distributional way of defining lower Ricci curvature bounds. So from before, I copied the expressions of the Ricci curvature tensor, or of the coefficient of the Ricci curvature tensor, and I will now drop regularity in G, and I will no longer assume it to be C2, but I will assume it to be continuous and to admit L2 log connection symbols. And then we see that this very expression locally just induces a distribution of order at most 1 on Rn. So that gives us hope we can distributionally probably evaluate the Ricci curvature tensor in with these regularity assumptions. Okay, so when we do distributions on Rn, what we usually do is we take a CC infinity test function, we take the distribution and we test it with the CC infinity test function. And oftentimes that involves integration, so now we're on a manifold. In Rn we usually integrate against the Lebesgue measure. On the manifold we have to do something different. On the manifold we will integrate against the volume measure induced by the metric G. And as we are interested in lower bounds of the Ricci, our test functions that we will multiply with the volume measure are not only going to be CC infinity, but also non-negative, because we want to get a sense of a lower bound, and then we need to test with positive objects or non-negative objects.
So can I ask a question? So for this, so where do the assumptions so that G is continuous and gamma is an L2 come from? So they're necessary. So L2 do you need in order to multiply? Yeah.
Yes, L2. Okay, the
C0.
C0 is technically, in order to define the Ricci curvature tensor, it would be enough to assume G is L infinity log, and the inverse of G is L infinity log as well. Mm-hmm. But later on in the talk, I hope to remember to point you to it when it comes to it. We will have to analyze the metric structure of the manifold, which doesn't really see the connection symbol, but really mostly sees the metric G itself. And then it turns out to be, for now at least, we don't know how to do it if G is not C0, because then the metric definition gets way more complicated. Mm-hmm. So yeah, it's a bit hidden why C0 is a necessary assumption, but the L2 log connection is the lowest we can assume the connection to be in order to still make sense of this object. Yes?
So what is this L2, what is the log thing mean?
The log means we don't integrate over the whole space, but we just integrate over compact sets. So L2 log says that if I pick any compact set and I compute the L2 norm only on that compact set, it's going to be finite. And that's enough because for distributions we always take compactly supported test objects, so L2 log is enough for us to have sense of these integrals. Are there any more questions? Okay, well then, we say for a metric G with these very regularity assumptions, so continuous and L2 log connection, that it satisfies Ricci curvature bounded below by a real number k if for every smooth vector field and every test volume as above, so some non-negative CC infinity function times volume form, we have that the Ricci curvature of twice the vector field tested against the test volume, and that, evaluated distributionally is bigger or equal than k times the integral over the inner product of the vector field with itself, integrated against the test volume. And so, as I said, this really boils down to distributional calculus on Rn, because as we are compactly supported, we can always pick a partition of unity that allows us to stay in one coordinate patch, or to have finitely many coordinate patches that we have to consider. And then we really boil down to distributional calculus in Rn and can deal with these objects just as we do it in Rn. If you're not too familiar with distribution theory, maybe the takeaway is we integrate by parts once and then we're happy. One more little thing about the distributional side of this is it is useful to introduce the notion of Sobolev spaces on manifolds, just as some sort of terminology and to identify certain objects. And in order to do that, I will just quickly recall the definition on Rn and then point out why it's exactly the same, so you don't really have to read the actual definition, but just get a feeling for it. So say we have a P in 1 infinity, we have a natural number k, and then we look at the space of smooth functions, and maybe we have a open set omega in Rn. Then we look at the smooth functions on omega such that the following norm is finite. So the sum of the LP norms over the first J derivatives has to be finite, and then the Sobolev space WKP is just the completion of all smooth functions for which this expression is finite under this very norm. That's how we get the Sobolev space WKP. And, well, just the exact same thing happens for a manifold. So we have one tiny change. Instead of, so on a manifold, we have to be careful about this because instead of the classical differentiation does not really exist on a manifold after a certain level. So instead of having a classical differential here, what we plug in here is the jth covariant derivative, which so basically takes into account what the metric G does to the manifold. And after that, it's the exact same definition. So we take smooth functions for which the first J covariant derivatives are P integrable and complete the whole thing with this norm. And that Sobolev space is going to be called HPK. And now, so this definition has been made for smooth metrics, but if we don't take too many covariant derivatives, so if we don't get to the point where we have to differentiate the connection, we can actually stay with, we can generalize these definitions to the setting that our metric is just continuous and admits an L-to-log connection. Yeah, and we will also mostly be interested in the case P equals 2.
But here you don't need for the second assumption, yeah? You don't need to assume something about Christoffel symbols in order to say what the Sobolev spaces are. Not really, but like when we get to the point of actually computing covariant derivatives of an object, we will at some point invoke the Christoffel symbols. Okay.
So in order to not get confused, also we don't really need this much except for basically k smaller equal 2. So yeah, I guess there would be a way to.
Okay, I use for k. Okay, for k. Sorry, then probably you're right. So not only for k equal 1.
Yeah, no, but we will mostly work with the k equal 1 case, so in that case you can ignore that. Okay, and now just to round up the circle about the distributional part, if you recall how the Ricci curvature tensor looks, the distributional Ricci curvature tensor in this case basically acts on h to 1 maybe cap L infinity vector fields. So as long as we test against objects of this kind, we can evaluate the distributional Ricci curvature tensor by the regularity assumptions that we've made on G. But yeah, don't worry about it too much. I'm not going to get into the fiddly details about exponents. That was it about the distributional parts. Again, takeaway, you can integrate by parts and still make sense of lower distributional Ricci curvature bounds. There's a second way to define lower Ricci curvature bounds. For more general spaces, which is optimal transport based, so I'm hoping to give you a very brief recap of optimal transport in case you haven't seen it before. And okay, the way to do it is now we stop thinking about any manifold structure or anything. What we do now, we look at a metric measure space. XD is a Polish space, so it's completely inseparable. And M is a sigma finite Borel measure. And we are interested on statements or on the space of Borel probability measures on X. Okay, later on, just to give you a flavor, later on X will be our manifold, D will be the distance induced by the metric G, and M will be the volume measure induced by the metric G. So that's how to think about these spaces. That's a very vast generalization of a manifold, if you like, of a manifold as a metric measure space, if you like to think about it. Okay, optimal transport gives us a way to define a distance between Borel probability measures in the way that we think, okay, I have this one measure, I have a different measure, and I want to transform the first measure into the other measure, keeping the cost low. The cost for now can be anything, but in this case, the cost will just be given by the distance squared. So, how are we going to do this? We take two Borel probability measures, mu and nu, and we define the set of admissible test plans as probability measures on the product space, such that the first margin of the measure equals mu and the second margin equals nu. And then, in order to compute the two Wasserstein distance, all we do is we take the infimum over all admissible test plans of the distance squared integrated versus the integrated against the test plan, the transport plan, and well, we have to take the square root for it to be a proper distance. So, yeah. Also, maybe don't worry too much about the technicalities. I will not actually use optimal transport. The takeaway here is there's a way to define a distance on probability measures that kind of respects the metric structure of the space. Okay, yeah, and one can prove that W2 is a metric, is a distance on those measures that have, we say, finite second moment. That just means that their W2 distance to some Dirac measure, and hence any Dirac measure, is finite. And, okay, so far, all of this only looks at the metric structure. We haven't really invoked the measure. From now on, we will be looking at measures with finite second moment that are also absolutely continuous with respect to our reference measure, M. And, well, you know, if a measure is absolutely continuous with respect to another measure, we can write it as a density times the measure. So we can write we can find a function such that mu equals rho m and rho is in L1 of n. Okay.
So this, if we're thinking of X as a manifold, the M is supposed to be the volume measure, roughly.
Yeah. Yes. Okay. Well, now, given some absolutely continuous finite second moment Borel probability measure, we can define the entropy as the integral over density times log density over against the reference measure, and if the integral is finite, if not, or if the measure is not absolutely continuous, we just set it to infinity. And now, this is what we need to define a very general definition of Ricci curvature bounded below for a metric measure space, which is also known as the CD K infinity condition. So CD stands for curvature dimension. K is about the curvature, infinity is about the dimension, but I will not go into detail about that. And it has been introduced by Sturm and Lott-Villani. And okay, we say a metric measure space, as before, has Ricci curvature bounded below by K, where K is any real number, if this entropy functional is K geodesically convex. So, what does that mean? That means we take any two measures with absolutely continuous, with finite second moment, then we ask that there has to exist a geodesic, so a constant speed curve, deforming the first measure into the second one onto the level, on the level of the metric space that consists of the probability measures with the Wasserstein 2 metric. And along that geodesic, we want this entropy functional to be K convex. So in the case of K0, this goes away, and that's just normal convexity, otherwise we get this little extra term. Okay, and you may be wondering, why on earth does this generalize? Ricci curvature bounded below. Well, it does, because for a smooth Riemannian manifold, the Ricci curvature tensor is bounded below by K. Like just in the classical sense with pointwise evaluation of the Ricci curvature tensor, if and only if the metric measure space consisting of M with the distance induced by the metric and the volume measure is a CD K infinity space. So this is a consistent generalization of the concept of curvature bounded below by K. And this really only uses the metric structure and the measure of the space. So this is great. We now have this identification for smooth Riemannian manifolds. Now the question is, do these definitions still agree if we drop regularity? So if we go to the point where we cannot evaluate the Ricci curvature tensor pointwise, so if G is below C2, do distributional and synthetic lower Ricci curvature bounds still agree? This is the question I want to focus on today. And, well, there have been some comparison results on that from 2022, and Kunzinger, Ober-Guggenberger, and Vickers showed that distributional lower bounds imply synthetic lower bounds for compact manifolds and C1 metrics, and the other way around for compact manifolds and C11 metrics. The result I'm going to talk about today is the theorem by Andrea Mondino and myself that shows that for a smooth Riemannian manifold, so only the manifold being smooth, and a metric that is continuous and that admits an L2 connection, we have that the metric measure space induced by that metric satisfies the CD K infinity condition, is equivalent to the distributional Ricci curvature being bounded below by K, and an extra volume growth assumption. So this volume growth assumption on metric balls that we can control the growth exponentially in this way. And I will comment on that volume growth assumption later on, because obviously we would like to drop that, so we just have a nice equivalence there, but that's only going to be at the end of the talk. And I'd like to mention that in 2024, independently, Kunzinger, Ohanian, and Barrabasso proved that distributional implies synthetic Ricci curvature lower bounds for locally Lipschitz metrics without any volume growth assumptions. Okay, and I want to give you a flavor on how we actually prove this. And okay, as you saw, maybe this whole optimal transport part seemed very ominous, and you may be wondering how you get from transporting probability measures to distributional calculus. Well, the way is to just understand the synthetic setting a bit better, because there has been a lot of work done, and that is what we are going to do. Okay, before you worry too much about this definition, just imagine you have a function that is in C1 on Rn, and you have a curve that is also C1 into Rn, and then just by the fundamental theorem of calculus, if you want to compute the difference of the endpoints. What you do, you can write it as this integral over the gradient of f times the speed of the curve. Okay, this is very easy. This can be evaluated for more general curves and for more general f's. This very heavily uses Rn. So what we can do instead, we put absolute values here, we get absolute values here, and then an easy way to estimate this term is to just compare the norm of the gradient times the amount of the speed. And this is a way to generalize first order differentials to more general metric measure spaces that do not have an underlying differential structure. So that's what we're doing here. We have any function, and we say any function f, as here, and we say a function g that is measurable and non-negative is a weak upper gradient for f if for almost every absolutely continuous curve, well, this inequality holds. As in general metric measure spaces, we can define the speed of an absolutely continuous curve. I think we've seen that in the winter school earlier. So this expression up there makes sense. Please don't worry too much about the almost every absolutely continuous curve. That is also just very technical and yeah. Okay, and once we have this definition, we can take the essential minimum over all weak upper gradients, which is still, that can be proved, a weak upper gradient, and that will be called the minimal weak upper gradient, and it's, yeah, it exists. And once we have it, we can generalize the definition of the Sobolev space W12 to very general metric measure spaces. So what we do now, we just say the Sobolev space W12 with this little W on the bottom, that means weak, is the space of L2 integrable functions whose minimal weak upper gradient is also L2 integrable with that norm, and that can be proven to be a Banach space. And once we have that, we can also generalize the idea of the Dirichlet energy to the Cheeger energy, which is given by a half times the L2 norm squared of the minimal weak upper gradient of the function. Okay, so these are nice notions. I mean, so far we don't really know how to use them, but they very much look like something we already know, just for way more general spaces. And yeah, maybe in the Rn case, this is even nicer. So W12 is not only a Banach space, it's a Hilbert space, and that's something that is heavily used all the time in functional analysis. So we would kind of like that too. Well, this is something we cannot generally hope for any metric measure space. So there is the notion of infinitesimally Hilbertian spaces, which are just exactly those spaces for which the Cheeger energy is a quadratic form. And these spaces open up a very powerful set of tools, because once the Cheeger energy is a quadratic form, every quadratic form extends to a bilinear form. That is straightforward. Then we can use integration by parts, or generalized integration by parts, to define some sort of Laplace operator that respects the quadratic form. Once we have a Laplace operator, we can write down a heat equation, and it has been proven that, well, there exists a heat flow like this, consisting of a submarkovian semigroup. Don't worry about that too much. Such that for positive T, the heat equation is satisfied, and such that the heat flow converges to its initial value in L2 when we send t to 0. So, and then I think hopefully the last bit of no, not quite, almost the last bit of definition is now if a metric measure space satisfies the CDK infinity condition and is infinitesimally Hilbertian, we say that it satisfies the RCDK infinity condition, the R being for Riemannian, and, well, CD still curvature dimension. Okay, that was, again, lots of technical terms. I'm now hoping to, if someone is confused, to maybe ease off a little. And that is by the following proposition by Andrea Mondino and myself. Let's go back to our setting. We have a smooth manifold, continuous metric, L2 connection. Then the metric measure space arising from that metric is infinitesimally Hilbertian, and the synthetic Sobolev space coincides with the classical Sobolev space as you would expect it, or as you would hope it. And what does that mean explicitly? That means, given a function f, the Cheeger energy of f is just 1/2 of the integral over the weak gradient of f, norm of the weak gradient of f squared, integrated against the volume measure. Then the Dirichlet form is basically just the L2 inner product of the gradients of two functions. Then integration by parts gives that the Laplacian of a function equals just the classical Laplacian induced by g, which equals minus the Hodge Laplacian, and is going to be given as 1 over square root of the determinant of g. And now I hope to do this right. It's now given like this, can you see this? With the Einstein summation convention. And, well, the heat flow just satisfies this equation weakly, and that looks way more familiar to what we know. So all this synthetic machinery just does exactly what we would expect it to do in the case of a manifold with a low regularity metric. Now the last bits of definition I'm dumping on you. So for the synthetic framework, one has defined test objects, which are given by, so the test functions are given by synthetic Sobolev functions, for which also the Laplacian is in L2, the gradient is in L infinity, and the Laplacian is actually even Sobolev. And so still synthetically Sobolev. But this is, again, a very synthetic definition. And the test vector fields are given by just linear combinations of test function times gradient of a test function. Now, as you will see in a second, these test objects, through the synthetic machinery, we can prove nice properties about these test objects in the synthetic sense. And luckily, we have that the heat flow also has some regularizing property. So for a function that is L2 and L infinity, the heat flow of that function for any positive t will give us a test function. So we already get that many functions can be approximated in L2 by synthetic test functions, which is so far so useful. And
so this does not use the T on a manifold. This is a general.
This is a general thing about infinitesimally Hilbertian. Yeah.
You use also about the curvature.
Yes. Yes. From.
Yeah, in this case, you are in the case in which you have a boundary. You are assuming that you.
Yeah, for this property, we need to assume RCD k infinity. But well, in the proof of our theorem, we will assume CDK infinity. We get the R for free by this proposition up there. Then we can use RCDK infinity. Then we get this machinery, and then we can work with that.
Sorry, so in the proposition, why do you need to assume L2 log connection?
Yeah, actually, we don't need that.
Ah, okay.
This identification of the Sobolev space can be done
Because
without
it's the standing assumption of the main theorem, right?
Sorry? Yeah, this is the standing assumption of the main. So,
okay.
Yeah, in order for that space to be interesting, we need the L2 log connection, but actually, that proof doesn't use derivatives of G, so it can be done without it. Yeah.
So does that the Sobolev space is the same? Is it true for every P or only for 2?
So I don't really know much about the synthetic Sobolev spaces for any P that is not 2, so I have no idea.
So what is the question?
So do the Sobolev spaces are the same? Are they the same for every P?
Yeah.
Yeah.
Yes, in this case, yes. Yeah. So for k equal 1 and matrix
Yes.
is continuous.
Well, yeah, I mean, yes, yeah, as we have identified, we can identify the gradient of the function with the minimal, with upper gradient, or the absolute, yeah, they're the same, that's true. But only for k equals 1. After that, we might get lost. Now we get to the last piece we need to conclude our theorem, which is what I've done so far was basically first order calculus generalized to metric measure spaces. Well, this can be done for second order calculus in RCDK infinity spaces. So Gigli has done that in 2018. And what he does is generalizing lots of things, generalizing the covariant derivative, the Lie derivative, Hodge theory, and then using Bochner's formula, there can be defined a generalized Ricci curvature tensor which maps these synthetic test vector fields, or which takes 2 synthetic test vector fields and gives us a measure, finite Radon measure on M, such that if we chose the same vector fields, it satisfies exactly what we want, so it satisfies basically Ricci curvature bounded below by K. Which this last step is from the identification that we've done here, that K times the inner product of B with itself times the reference measure in our case is just K times, inner product of B with itself with respect to the metric times the volume measure. And, factorizing that whole machinery and using these identifications, which basically say all these synthetic notions do exactly what we want, this remains true. So in local coordinates, this Ricci curvature tensor, this synthetic Ricci curvature tensor looks exactly the same as the distributional Ricci curvature tensor, which is almost what we want, so we're almost there. The only problem being that this only holds for synthetic test vector fields, but in the distributional case, what test object do we use? Well, we use CC infinity test functions, vector fields, volumes. So now, the only big thing that needs to be done to conclude the theorem is to bridge the gap between synthetic test objects and distributional test objects. And that is going to be done in the main step of the proof. I will quickly run through the sketch and then I will perform the main step, which is going to be purely analytic. So even if you're absolutely not familiar with RCD, you can understand that part. And, well, the way we're doing it is maybe need a little bit of space on the blackboard. Okay, so the way of doing it is we assume CDK infinity. We get the R for free because we've identified the space to be infinitesimally Hertzian. So we are from RCD infinity and we want to go to distributional lower bounds. So first thing we do is we look at the test objects in the synthetic case. And we look at the test objects in the distributional case, which is CC infinity of, say, the tangent space. And we want to go from here to here. This was given by function times gradient of function, and these functions have to be test functions in the synthetic sense. So we define something in between. We define the space comp V as the linear span of function times gradient of function, but at this time these functions will have to be CC infinity, so they are somewhat in between these two. Okay. Then, what we do, in the main step, we prove that comp V is dense in here, in the sense that it is dense in H11, and we can bound it in H1 infinity, so it's going to be dense in H1p for every p smaller than infinity. So, the main step is proving that this is dense in here in a suitable norm that looks at the vector field itself and at its first derivative. Because that's what we're going to need. A Ricci curvature is a distribution of a priori order 1, so we want to approximate the thing itself, first derivative, and we're on the side of safety. Okay, once that is done, say we have something that looks like this. What we do then, we use the properties of the heat flow to prove that taking this guy and applying the heat flow to both parts that this approximates this guy in a suitable way. Then we get ends here. Okay, and once that is done, we're happy because we have that synthetic test objects are dense in a suitable way in distributional test objects. Then we can use this identification, pass to the limit, and get the lower bound for the distributional case. Yeah, we can conclude, because the Ricci curvature tensor, the distributional Ricci curvature tensor is a distribution of order at most 1, and, well, the density we prove looks at the first order. So that is good. I now want to demonstrate in a very simple example how this main step is done, because this is really purely analytic, forgets everything about manifolds and geometry. Is like a very analytic proof, and I'm not going to do the whole thing because it will get technical and fiddly at some point, but I want to convince you that this is true with a nice example, and for that one, we forget about manifolds. We just take a vector field on Rn, and, well, it has to be a vector field, so it looks like this. And we're now only going to work locally, so we're going to see how a construction like this can locally get us to something like this in the H11 form. Okay, how this is done is, well, fix a point, and maybe let's do this R2. The point is the origin, and we say that our vector field looks like, well, takes the value for 2, and the Jacobi matrix of this vector field takes this value. So, yeah, just simple example. Now what we're doing in the first step, we want to approximate x, so we want to approximate this without messing with this. So what we do, well, look at the function that sends R2 to R, sends xy to 4x plus 2y. Well then, the gradient of this function just equals our vector field x, and the Jacobi matrix of this gradient, or the second differential of that function, is 0. So what this function does, it approximates x on the level of the vector field itself, but it doesn't really mess with the Jacobi matrix, which is nice, because now we can look at the Jacobi matrix separately. And, well, this is already a gradient. This is not yet comp v, because this is not CC infinity. This is so far just C infinity, but in the end, cutoff functions will do the job, and we can basically use this idea to do that rigorously for comp v, to get to comp v. So, in order to approximate dx, what we do is we define the function rho that sends xy to y, and eta that sends xy to 3x. Then rho nabla eta is this vector field, and the Jacobi matrix of this one is just what we needed.
Could you read more of it?
Sorry? Oh, yeah, sure. Actually, I think I have to do this. But, yeah. This is what I wanted to do. So, this is the way. Now the Jacobi matrix of this guy, well, takes the same value as we wanted it to take, at our point P at least. And this vector field, well, it is not 0, but it is small because P is 0, so Y will be very small in a neighborhood around 0. And, well, this is just the idea. This has to be done rigorously. We have to explicitly choose, or like almost explicitly choose, a very certain partition of unity. We have to choose suitable cutoff functions. to make this rigorous, to make all of these guys not just smooth, but CC infinity. And then we can actually perform this main step and prove that we can find a vector field that is in conv that approximates any CC infinity vector field in W1P or NEP. Then, well, yeah, heat flow theory will be applied, and in the end, we get our result as sketched before. Other questions? Okay, then just a little outlook on more general versions of this theorem is, I did not tell you the whole truth, so the CDK infinity condition, as you may have maybe suspected, the infinity can be replaced by something finite. So actually, for a manifold, we can use any parameter that is real valued and bigger equal than the dimension of the manifold. We can still choose any real number k, and we don't only have to consider the volume measure, but we can multiply it with a positive weight that is given by e to the minus v for now for some smooth functions. Then you can define a way more complicated CDK infinity condition that I'm not going to write down. And that one is also optimal transport based, measure displacement convexity. And it is equivalent in the case of smooth manifolds to modified Ricci curvature tensor being bigger equal than k. So there is the theorem I already showed you actually does apply for weighted manifolds as well. That can be done very easily. In this case, the Ricci curvature tensor looks like this, so it takes the Hessian of minus the logarithm of the weight into account. And in the case of finite n, we get this extra term, which adds some difficulty because there is this nonlinearity in here. And also, just a quick comment, in the case that capital N equals dimension, we assume the weight to be constant, otherwise that definition doesn't make sense. Well, so there is such an identification of a more difficult Ricci curvature tensor and a more difficult curvature dimension condition, but we can prove the exact same theorem for that case as well. Same regularity assumptions on G, and the additional we have to make some regularity assumptions on capital V to still make the Ricci curvature tensor work and to have a sense of measures that is sensible. So we have to assume it to be C0 and W12 log, and then we get the same equivalence between the CDKN condition and this different Ricci curvature tensor bounded below by k with the same volume growth assumption we had to make earlier. Okay, and just like a very quick run through how this is done. This strongly uses the Berkeley-Emery condition, which has been proven by Sturm and Andrea Mondino to be equivalent to the RCDK infinity condition, and the Berkeley-Emery condition gives us this inequality about the Ricci curvature tensor evaluated at gradients of synthetic test functions. And this is also not quite what the Ricci mu-n tensor looks like, but it can be deformed. At least in the smooth case, it is very easy to see how to get from this to the Ricci mu-n tensor. And the way for us to prove it is, well, one can prove that RCDKN implies RCDK infinity. So we already get, with the previous theorem, that our Ricci curvature infinity tensor is bounded below by k. Then we can generalize the concept positive distributions are measures to matrix-valued positive distributions, and yet that the Ricci curvature is actually given as a measure, which makes many things way easier, because once we know that, we a priori do not know that, but with a previous theorem we get that, this guy only sees the values of the vector field and no longer takes into account first derivatives of it. So that is very helpful. And once we have that, we can locally choose functions f that have the property that are the Hessian of f is almost diagonal, so we can compare this guy, and that will eventually, doing some computations, lead us to the Ricci mu n tensor being bounded below by k. Then, yeah, we'll have to do some more elaborate partition of unity work, and we'll have to use the Besekovich covering theorem to do that, so it really does get a little fiddly, but it can be done, and that's how we conclude for the finite n case. And now, just for the very end, on the volume growth condition, for now, in both theorems I've showed you, we had to assume this exponential volume growth condition. This is already implied by RCD. Just in order to go back to prove distributional implies RCD, we have to make this assumption. And, well, luckily we can drop it, at least in many cases, which is if the metric is in W1P log for any p that is bigger than the dimension, and if the weight is constant, and of course the Ricci curvature has to be bounded below k. This can also be dropped, like if we want to have a non-constant weight, we need to assume that the weight and the metric are both C1, then we can also prove that the volume growth assumption is implied. So in those cases, we get the full equivalence without making extra assumptions on the volume growth condition. Yeah, but especially the case W1P is very recent and to be uploaded. Yeah, that was all I wanted to say. Thank you very much for your attention. These are the main references to that exact question.